need to record the rules. So just a few reminders about things. Mute your microphone and keep your video turned off throughout the presentation. The buttons on the bottom should be in red. Please make sure that you're utilizing the chat function on the right-hand side of the screen to ask any questions. We will be doing a Q&A in the last 10 minutes or so of the presentation. I'll ask Dr. Jowitt those questions. Also, if you have any issues, you can access the Google Meet Help Center. That's the link on the screen right there to check out if you have any issues. If you're having issues with sound, post them in the chat and I might be able to guide you through them as well. Also, again, we are recording. The link below is where today's presentation will be available for viewing after we finish today, probably within the next week. My name is Corey. I work in the College of Sciences. I'm the Director of Development. Thank you again, everyone, for joining us today. Before we get started with Dr. Jowitt, I want to let you know about next month's lecture. So we will be featuring Dr. Ashkan Salamat, Assistant Professor in the Department of Physics and Astronomy, who just made a very interesting and significant discovery regarding superconductivity. And so his topic will be the future of energy, exploring superconductivity at room temperature. So hope you can join us next month on November 25th. It'll be at 12 p.m. Virtually as well via Google Meet. So without further ado, I want to introduce our speaker for today's session, Dr. Simon Jowitt, who is an assistant professor in our geoscience department. The topic for this month's lecture is Who Needs Mining and Who Does Mining Need? Insights into how mining supports modern life and how economic geology research can help the mining industry. And just as a little background on Dr. Jowitt, Dr. Simon Jowitt is an economic geologist who is currently an assistant professor at the University of Nevada, Las Vegas. He has a Bachelor's of Science degree in geology from the University of Edinburgh, and a Master's of Science in Mining Geology from the Camborne School of Mines, and a PhD from the University of Leicester, all in the UK. Prior to joining UNLV in 2016, Simon spent 8 years at Monash University in Melbourne, Australia. I may have pronounced that wrong, sorry, Simon. Initially as a postdoctoral research fellow focusing on magmatic sulfide systems. His research interests are broad, but are focused on ore deposit formation, critical metal resources, and the security of supply of the critical elements. He also studies the use of geochemistry to unravel geological processes in a variety of settings with direct application to mineralizing systems, igneous petrology, and mineral exploration, global tectonics, and the links between magnetism and metallurgy. He has extensive expertise in mineral economics, metal criticality, and the economic side of economic geology, and has several recent publications on global, I don't know if you say the letters or if you actually pronounce them, but Cu, Ni, Co, PBZN, platinum group element. You want to?
Just global metal resources. It's
global metal, okay. Okay. And rare earth element and indium resources. So Simon has published more than 75 scientific papers and peer-reviewed book chapters since 2010 and was awarded the Society of Economic Geologists Waldemar Lindgren Award in 2014. This annual award is given to a young scientist whose published research represents an outstanding contribution to economic geology. We're very excited to have Dr. Simon Jowitt with us today, and without further ado, I will turn it over to you.
Thank you, Corey, and I'll give you a shorter biography next time, perhaps.
You're fine. You have a lot of accomplishments. We need to celebrate those.
Let me just bring the presentation up. Here we go. Okay. Everybody can see this okay? I guess you're the only one who can tell me, Corey, so.
I can see it great, yep.
Perfect.
Just a reminder before you start, Simon, if people want to pin to the screen, if you hover over the presentation and push the TAC, that will make the presentation the main feature. Go ahead.
Thank you, and thank you for the introduction. Yeah, today I'm going to be talking about, as the title says, who needs mining and who does mining need? And I'm going to start off with a kind of a deliberately provocative slide, which basically shows a large hole in the ground, Bingham Canyon, just outside Salt Lake City, and says, mining is old, dirty, problematic, and we don't need it, right? And I think, unfortunately, that's a kind of a common misconception of a lot of people, certainly in the general public, is that mining is an old industry. We don't need it anymore. Why are we still mining things? And one of the main aims of this talk is to kind of refute that almost entirely. So, who needs mining and who does mining need? And if you answer the first part of that, this question here, mining is old, dirty, problematic, and we don't need it, right? If you answer that yes, I'm afraid you're wrong, to be blunt. And the answer to the first part of this question, who needs mining, is basically everybody. But comparatively few people acknowledge that. Comparatively few people even think about it. It's one example of this is the United Nations 2002 World Summit on Sustainable Development. Direct quote here: mining minerals and metals are important to the economic and social development of many countries. Minerals are essential for modern living. And that applies even more today, and there's various other bits of information you can see about how mining links to sustainable development at the UN website here. But what I'm going to kind of start off with is by saying is, mining has been vital to modern life and society for centuries, and it's going to be this way for the foreseeable future. We as a society require mining to have the standard of living we've come to know and love. But one point is, but mining is dirty and harms the environment. It harms people. Perhaps it does. I mean, certainly there's a lot of legacy mining sites around the world that you can see that are still problematic today. But a lot of those are from the past, and mining companies certainly do a lot better job of environmental assessment, cleanup, remediation, and the like. And they're also more socially aware. Mining can also be beneficial to communities, both local and national and globally. Things are improving on this side, but certainly, as I said before, if we don't have mining, we don't essentially have modern life. And that goes into the future as well. I mean, people are talking a lot about climate change. There's a lot of talk with the coming election about the future of energy here in the US and globally. But if you actually want to do anything meaningful about hitting climate change targets, limiting carbon dioxide emissions, you need mining even more. And I'll show data to back up this claim shortly and kind of discuss as part of this who needs mining part of the talk. What about the second part of the question? Who does mining need? One thing I would say is mining obviously needs skilled people. That goes without saying, but they also need to be a bit more than just skilled. Geologists, geoscientists, the type of people we produce in the Department of Geoscience at UNLV, they've got roles throughout the mining industry, from exploration to mining to mineral processing to environmental impact remediation, the economic side of the business. The geoscientists form a valuable part of the mining industry, and I would argue certainly the type of people that mining needs. Equally, it's not just the kind of core skills that they have that make them valuable to mining companies or the mining industry or the government, counterparts to the mining industry. But it's important to recognize that if you're an exploration geologist, you can often be the first person from that mining company to work in a given area. You need to be conscious of social and environmental impacts. You need to actually acknowledge that you're working in an environment that certainly may be foreign to you. There may be different kind of approaches that are needed. So you need to have core skills in your subdiscipline of geoscience, and that's the type of people the mining industry certainly value. But also you need to have a knowledge that extends beyond that. And I would argue, economic geology and economic geology education is a key example of that, because we don't just think about rocks and minerals and the way they form, but we also think about the kind of environmental impact of mining, the social impact of both positive and negative of mining. And it's something I certainly talk about in my teaching role and research role at UNLV. So with all that in mind, what am I going to spend the next 40 odd minutes talking about? I'm going to talk about two main things: the role of mining in modern society, the role of mining in combating climate change, basically trying to summarize why we need mining. And secondly, the role of economic geology teaching and research in mining. Who does mining need, and how do we ensure the people that come out of it with a degree at UNLV in geoscience actually know something about mining and beyond just how the rocks form. Certainly, I'm happy to take questions at the end of the talk or after if people have to leave early. My email is here, and you can also catch me on social media on Twitter. If for those of you tweet it, so for those of you who are so inclined. So this is, who needs mining? The first few slides are going to say that all of us need mining. Every American born is going to use about 3.19 million pounds of minerals, metals, and fuels in their lifetime. There's the obvious ones like petroleum and natural gas for energy. But equally, every American born in 2020 is going to use about 2,500 pounds of aluminum or aluminium, if you prefer, if you're from the UK like me. Lots of clay, lots of iron ore, lots of lead even now, lots of phosphate, often used as a fertilizer. So this is material we mine and then we actually use for agriculture. Salt, stone, sand and gravel, zinc, copper, gold, lots and lots of other minerals and metals that are maybe used in small amounts, but that are vital to the things we consider part of our everyday life nowadays. Why is this the case? I mean, one example is, modern technologies have become more mineral intensive. Here we have a rather example version of a rather unsmart cell phone. And that the elements here that I kind of highlighted are some of the elements that are incorporated into this phone. If you look at a modern day smartphone, the range of elements we extract and use and incorporate into modern technology has vastly increased. And all of these, in the vast majority of cases, have to be extracted by mining. We'll discuss potential recycling, we'll discuss things like that later on, but the vast majority of material you see here is extracted by mining and is incorporated into what we consider modern technologies and just routine. Everybody in this, everybody's listening probably has one of these in their smartphone in their hand or thereabouts, and so this is this means that minerals, especially in this case, are just part of our everyday life. It's not just smartphones. I mean, here's just an example of breaking down the elements of a smartphone. You've got indium and tin, which enables your touch screen. You've got glass, which includes aluminum, silicon, potassium, lots of rare earth elements involved in the coloration of your smartphone and so on. There's a huge variety of different elements that are combined to make your smartphone smart, to make it user-friendly, to make it do all the things we have routinely come to expect this technology to do. And the same apart, this is another example, looking at the rare earths again at this, in this example, here's a typical home. Where do we use the rare earths? We use them in fridges, any consumer electronic that has a very powerful magnet, like a hard drive in a laptop, uses the rare earths. Circuitry, color displays, batteries for hybrid cars, glasses, all these things use this range of elements called the rare earth elements. And this is just one subset of the elements we extract by mining and we use. Same applies. This is an example of a car. You could just talk about an all petroleum car with copper wiring, with a steel body and so on. But then if you actually start to look at hybrid and electric vehicles, the amount of minerals or the mineral intensity of this transportation actually increases significantly. Lots of rare earths in things like hybrid and electric motors. The LCD screens typically use some rare earths and so on. And the same applies to, if we just take a wind turbine. The US is actually uptaking quite a lot of wind energy. Even states like Texas have a significant proportion of wind energy production now. And if you look at a single wind turbine, you're talking 3 tons of aluminium or aluminum, nearly 5 tons of copper, 335 tons of steel, 1,200 tons of concrete, 2 tons of rare earths, zinc, moly also as well. All of these materials, especially things like the rare earths, which are recycled at very low rates, have to be obtained by mining. The vast proportion of the material you see in this wind turbine, as an example, is derived from mining, from primary, the extraction of metals from minerals that are found in all deposits. So that's just a few examples of many. You can just look around you, whatever room you're in, there's going to be things, that even the building you're in, all of these things require metals and minerals. We often take them for granted, but this means that mining is a fundamental part of everyday life, the material basis of modern society. And this is the reason why we currently mine more minerals and metals than any other time in history. Population growth combined with basically a demand for a high standard of living means that everything we do is more mineral intensive. We could recycle these metals. We do recycle these metals. Certainly some metals are more recyclable than others, but not all of metals can be recycled. It depends on their use. Phosphate and fertilizer is a dissipative use. You can't recycle that. It disappears once used. Rare earths in your smartphone are very difficult to recycle because they're used in such small amounts. And recycling is very well and good, but it can't always meet increasing demand. If you've got the significantly increasing demand for one element that isn't really present in a lot of consumer goods that get recycled, means that that increased demand cannot be met by recycling alone. We have another slight problem in that metals we mine out of the ground and use, they're not really substitutable. We found very little in terms of very little substitutes, or very few substitutes for copper in wiring that have the same level of efficiency, the same amount of cost, and so on. And these are just a few examples of how mining has increased over the last 100 plus years. This is gold production, obviously very close to home here in Nevada. We're the US's largest gold producer. This just shows the kind of how gold demand has increased over time. Back from the 30s and 40s, back up to the early 1980s, then you get a significant ramping up of gold production to more or less present day levels at above 3,000 tons of gold a year. The same applies to any metal you look at. Here's copper. Copper back to the 1900s, we're producing less than 1 million tons of copper a year, all the way up to today, we're producing this. If you plot this graph up to the present day, you'd hit 20 million tons of copper a year. This zinc is the same. This applies over and over again. You see a consistent increase in demand for metals as a result of increased population, but also just as a function of the way we live. Modern living requires metals, and that means that we currently mine more metals and minerals than we have done at any point in humanity's past. We're reliant on mining as a society. So that's fine. We mine a lot, but why can't we recycle these metals? We do. We recycle a lot. That meets some demand, but not all metals can be recycled. Recycling cannot always meet increasing demand. Metals and minerals can't be substituted for each other. The way we use certain metals, certain minerals is almost unique. You cannot, say, easily replace copper with aluminum in wiring without losing some of the characteristics that make copper so good at conducting electricity. So, this is data from the UN looking at typical end-of-life recycling rates. Anything shown in red is an element that we use, maybe not in huge amounts, but it's something we use in modern electronics or modern consumer goods or something else that supports our way of life, but is recycled at a rate of less than 1%. So, all of the rare earths, a lot of these elements like zirconium, hafnium, certainly lithium, used in batteries, all of these elements are recycled at rates of less than 1%. We're better at recycling some of the base metals like iron, cobalt, nickel, and copper, but even then, you will never get 100% recycling, and recycling cannot always meet increased demand. And these data just show the substitution or the substitutability of the elements. The more you tend towards this color, the worse you are. We basically can't find substitutes for some of these elements. So like things like manganese, yttrium, and magnesium, they're very poorly substitutable. We can't find the other metals that replace the characteristics that these metals impart to whatever we're putting them in. And it's also important to realize that, okay, well, praseodymium, neodymium, these are fairly substitutable. But what you substitute, what do you replace neodymium with? Another rare earth, basically. You can't replace it with a random element. It's replaced by another rare earth, which also has issues around how we extract them and how we use them and so on. So that's a kind of brief outline of why we need mining. It's the fundamental basis of our society. It's where we get the raw materials that enable modern life to occur. That's been the way, that's been how it's been for centuries. It's not going to change. unless something really off the wall happens, and that's pretty unlikely. One other thing I wanted to say is, some of you might be thinking, hold on, you showed an electric vehicle and a wind turbine. Why are you showing that? Surely you're not going to link mining with climate change mitigation. Well, yes, I am, actually. One of the things we need to think about moving to the future is climate change. And one of the things that have been increasingly argued is if we have any hope of meeting carbon dioxide emissions targets as a country, globally, we need more mining. We need to produce more metals that can be going to things like solar panels, electric vehicles, and wind turbines. All this infrastructure we need to reduce carbon dioxide emissions targets. This is happening already. People are moving towards electric vehicles, hybrid vehicles. People are moving towards renewable energy. I think there was a survey today that came out. I listened to NPR that said something like 80% of the US thinks that 100% renewable energy generation is a good thing. So even if you don't agree with the arguments about climate change or the data behind climate change, the evidence there, this move is inevitable. It's happening already, and it's going to continue to happen, either by litigation or just by consumer demand. So this materials intensity of our society is going to increase as a result of us moving towards electric vehicles and renewable energy. And the metals shown in the next few slides, the implications of this are just a selection of some of the thinking that's going on in this area. These slides are mainly taken from modeling by the World Bank to show what we need to do if we want to hit certain emissions targets by uptake of solar panels, wind energy, and electric vehicles. And if we look at, this is just for wind turbines alone. So what we have here is a variety of different metals, the percentage change in basically the demand for metals, just as a function of producing wind turbines to keep basically warming to 4 degrees higher than it is now, or 2 degrees higher than it is now globally. So this is fairly extensive climate mitigation. This is somewhat extensive climate mitigation. If we go this route for the wind turbine, proportion of energy, green energy that we need to hit emissions targets, we need to increase zinc production by 150%, nickel, and so on. If we want to produce enough wind turbines to make the wind proportion of say 30% of energy generated by wind turbines. I don't know what the numbers are, but it's something like that in these models. We need 250% more copper than we're currently producing to meet this wind demand for wind turbines alone. Never mind solar panels, never mind electric vehicles. If we look at an individual element, hopefully here we go. This is neodymium. Rare earth element. It's used in magnets in wind turbines, used in magnets in electric vehicles, used in magnets in laptops and hard drives because it makes those magnets essentially stronger. So what we have is current annual neodymium production of about 7,000 tons a year. If we go, basically, if we're trying to emit, this is the lowest target, this is the highest target, where we're going from kind of 10 to 50% of capacity by 2050. And what we're talking about is the cumulative demand for neodymium being like 400,000 tons up to 250 to 2050. In other words, what we need to do if we want to hit any sort of energy generation targets relating to wind or solar or electric vehicles is we're going to need to mine a lot more of a variety of different metals and minerals. This just shows for electric vehicles. This is predictions to 2030. This is only 10 years away. This is predicting the demand for metals in the battery packs in electric vehicles, just the battery packs, not the other wiring, not anything else in these electric vehicles. But this is just the demand increase from about the present day here through to here, just for the lithium battery packs in passenger electric vehicles. This is going to happen, not because, one, because people are thinking about climate change, but two, because people are moving to electric vehicles. It's a change in consumer demand. And that is going to impact significantly the mining sector, because the mining sector is the thing that's going to have to produce all of this. Certainly things like lithium and graphite, these materials and minerals, these metals and minerals are not recycled at a very high rate. So we need to actually think about, if we're going to meet these targets, we need to think now about where we're going to do this mining, how we're going to do it, what we need to extract. The thing with mines is that they take a long lead-in time to get developed. So if we want to hit targets like this, like certain targets that the countries like the UK are saying we're going to be all electric vehicles by 2050, we need to think about this now. We need to think about how we can ensure our modern way of living is sustained, what sort of mining we need to actually do that. And the bottom line is, the data shows, a lot of data is that if you want to do anything meaningful about climate change, you're going to need to mine more metals and minerals. And that creates other questions and problems, opportunities to think about where we're going to find these metals and minerals. We need to understand the geological processes that form mineral deposits, especially mineral deposits we haven't thought about much in the past. Like lithium deposits, rare earth element deposits, these things that form important components in green technology or more efficient technology. We need to increase the efficiency, there should be no efficacy, but efficiency of mining in terms of recovery and energy use. We need to think about what the waste material from past mining, can we extract metals from this and so on. We need to think about what impact this metal extraction is going to have, the environmental impact, the social impact, and governmental impact and benefits, the risks involved in all of this. And one question is, how can we do this? And I'd argue we need education and discussion. People need to realize how vital mining is. It's all right saying we need to do something about climate change, but actually to do something about climate change, you need to have these metals. You need to have these raw materials that are going to form the basis of a low carbon emission society. And if we can't do that, we need to weigh up the balances, the pros and cons of if you can't have low carbon society without having mining. You can't argue for one without arguing for the other. That's the argument that I think a lot more people need to hear. And if you've not already been convinced, I can go on and on. I could take probably the next 2 hours, but I think Corey would cut me off. But I'd emphasize again that every single person listening to this talk needs mining in one way or another, or probably in multiple ways. The device you're listening on, the device you're watching this talk on, the electricity that's powering that device, the car you drive, the house or apartment you live in, all of the modern conveniences you take for granted require minerals and metals that need to come from somewhere. And if you want a sustainable future with a reduced anthropogenic climate change, lower carbon dioxide emissions, it's going to be built on the back of the mining industry. It has to be. There's no point having electric vehicles that are fueled by electricity generated from coal. If you have that, the impact of that vehicle, modeling suggests it's worse than just having a gas vehicle. So what's the point? You need to actually have electric vehicles fueled by renewable energy. And if your attitude is, well, climate change doesn't exist, that's, this isn't a climate change argument, but one thing I would say is the world is moving that way anyway. Renewable energy, electric vehicles are the future. This is the chance for the US and Nevada to be a world leader. Demand for these metals is going to increase. Can we, as a state, as a country, be the supplier of raw materials and the home of high-tech manufacturing? That's the opportunity. You can argue all you want about these changes in demand. The fact is there's an opportunity there, and I strongly suggest we should move forward and take it. But that's just my viewpoint. So that's who needs mining? Who needs mining now? Who's going to need mining in the future? The answer is every one of us, and that answer, is going to become increasingly important if you want to do anything about carbon dioxide emissions, about anthropogenic climate change. The second half of the talk is, who does mining need? I would argue that mining needs skilled people who can fill roles in industry and can answer key research questions. The skilled people who can work in industry, who can work in government, who can work in research to enable the mining we need and will need into the future to happen. Problem solvers who can work across disciplines and outside of mining. People have more than just technical skills as well. The biggest risks faced by the mining industry in the future are likely to be environmental, social, and governmental, not necessarily geological, not finding the material. That might be the case of some elements, but certainly the environmental, social, and government risks and challenges are going to be major. And that means we need to educate people. We need to educate people about these factors, about environmental, social, and governmental issues, as part of economic geology teaching and research. So people going into the mining industry actually know about these things and can think about them rather than just basically learning about rocks, which is important, but they need to learn about other aspects of the mining industry and mining as well. Selling our aim at UNLV, selling what I believe in, the way I try and teach and do research is to do all of the above. But one thing is, I mentioned questions here. What about these questions that I mentioned? There's just a selection of questions that I think and for reasons I'll explain shortly, that these are just a selection of questions about the kind of type of people that mining needs, people who can think about and can answer these questions. Where should we explore for new mineral deposits? How should we explore for them? How do mineral deposits form? How can we use this knowledge to find new areas to explore? How can we extract more metals from mineral deposits, increase efficiency of extraction? How can we, what are the environmental impacts of current and legacy mining sites? What happens to metals after they're mined? Where we're going to produce metals from in the future? What risks does mining face? In other words, the people, the skilled people that can work in every facet of the mining industry. And what I'm going to do is I'm just going to give you a few examples of how basically researchers in the past have answered some of these questions or have thought about them. This is going to be a whistle-stop tour through research. I can provide more information and more papers on all of these topics after the talks, for sure. So if anybody's interested in any specific aspect, they can email me and I'll get back to them. But I just want to give you a whistle-stop tour of the type of thing that people, geologists in the mining industry, geologists in academia, geologists in government and other areas of society, all these working with mining, think about and how we can answer these questions. So, for example, where should we look for new mineral deposits? Here's one example. This is the high Arctic, is the US and Canada. So this is Alaska. This is the far north of Canada. What we have here is these kind of red, orangey colored rocks, which are what's formed part of what's called a large igneous province. These provinces are often prospective for nickel. And what we can do is we can actually use the geochemistry, in this case copper, the geochemistry, the concentrations of elements in the rocks we're looking at, to work out which of these rocks are actually prospective to host nickel deposits in this case. This is just one example of how research and exploration can dovetail together to enable us to find new mineral deposits to meet, in this case, nickel demand in the future. Similarly, we can understand, this is a cross-section through the Earth, essentially, from the crust down to the mantle. The details are not hugely important, but what we have here is a whole load of magmas making their way through the crust, interacting with the crust, and we can use models like this to understand the links between geological events and the formation of mineral deposits. It's like a predictive model. We can say, well, if we have mineralization forming in this area here, then this is the type of thing we can look at. We can understand links between geological and magmatic processes involving magmas, and the formation of mineral deposits. We can look at how plates have come together in the past. So this is just a reconstruction. This is Brazil, Suriname, Guyana. So this is South America. This is Africa. This is a few million years ago, before the Atlantic opened between the two, when what you had was a contiguous, basically, area of geology. And what you can do is you can look at the geology on one side, all these dots are gold deposits. Lo and behold, we have contiguous geology with gold deposits on the other side. So again, we can use this kind of reconstruction relationship to understand where we should look for new mineral deposits. And again, this is how research and exploration and mining can dovetail together. We can use new approaches for the more localized examination and working out where mineralization might be. These are just contoured maps of different concentrations of elements that relate to or highlight the areas that are prospective for mineral deposits to be found. What we've got here is we've got basically a numerical approach to understanding the distribution of these elements and locating maybe new discovered copper occurrences, in this case, in these areas here that were identified using new approaches to interpretation of data that we're using in mineral exploration. And we can actually take this a step further. We can make 3D models to actually understand the distribution of areas that are interesting for mineralization, not just at the Earth's surface, but also underground using a variety of different data and things like machine learning to actually enable us to interrogate data better to understand where we might find new areas of mineralization. We can also understand how mineral deposits form. These are two examples. This is a mineral deposit in Australia where we have basically nickel mineralization forming as a result of hot fluids circulating through the system, so-called hydrothermal fluids. This is an unusual type of mineralization that forms the basis for exploration in other areas where we might find similar mineralization. And similarly, this is from South Africa. We have examples of magmatism that forms mineralization and the various stages involved in that formation of the mineralization. Both of these can be used as guides for exploration in areas that might host similar mineral deposits. And we can do this closer to home. This is research that one of my PhD students is undertaking at the minute, looking at certain rock type called pegmatites in southern Nevada and into Arizona, and that host a variety of different elements, and basically looking at forming models and testing models for their genesis. Whether we have, for example, a granite down here that actually forms these pegmatites. That's one model for them. Here's another model where basically you have melting of crustal rocks as a result of heating, and that forms again these magmas that can form these pegmatites. So what we have is different models that we can actually go out there and test, determine which is more applicable, then use that to inform how we can understand where to look for new mineral deposits. It's important to understand if you have a mineral deposit, the relationship between the metals you might most be interested in. Like if we have a copper deposit, for example, or a nickel deposit, if people talk about nickel deposits, about zinc deposits, but it's important to realize that a lot of the other elements we use are actually sourced as byproducts from those copper deposits, zinc deposits, lead deposits, etc. These relationships are going to be increasingly crucial as we move towards, given the number of elements we use in modern technology and the like. So that if you use a copper deposit, we need to start thinking about, okay, well, we're going to produce copper, but are we going to produce selenium and tellurium? Can we produce molybdenum, cobalt, rhenium? All these other elements that are important in a variety of different end products, end uses, commercial products or transport or whatever. But we need to think about how we can actually understand these relationships and maybe increase the efficiency of extraction of these metals. Where are they? How are they associated in different mineral deposits and the like? And we're doing that as well. This is an example of one of my postdoc I'm employed at the minute is currently looking at global mineral deposits as potential sources of tellurium, trying to identify where this metal that's key for things like solar panels can be used, where it might be sourced from in the future, what deposits are going to be very important targets for future tellurium extraction. And you can do this for all different types of co and byproduct metals that are important for green technology and things like this, but we don't exactly know where we're going to get them from in the future. We know they're in mineral deposits. We need to understand their distribution in order to extract them. And we can also look at mining waste. So this is an example from Australia this time. This is a mining waste produced by the mining of the famous Broken Hill deposit, a lead zinc deposit in Australia. It produced lots of lead, lots of zinc, but it also contains quite a lot of indium, which is vital for touch screens. But that indium was never produced. There was no demand back in the 1800s, the earlier parts of the last century. There is demand now. So what we can do is we can say, well, how much this metal is there likely to be in the tailings that are just sitting there on site? And if you actually look at the lowest amount might be 500 tons of indium. The highest amount might be 3,500 tons. I think we produce about 300 tons of indium a year, so there's about 2 years global indium production minimum just sat there in mining waste. So we've got that as a potential target. We need to think about how we can use that in the future. How that may also do things like enable the environmental remediation of sites that are problematic. And we can look at the rocks in detail. This is a mineralization from Australia, but here we're looking at different minerals, their contents of different elements. understanding how we can actually process these ores to enable the extraction of the metals we're interested in. So this is developing processes to maximize extractions. This is what we call geometallurgy, which is a burgeoning branch of research between economic geology and mineral processing. On the other side, so we've kind of gone from exploration to production. We want to actually understand things like the environmental impacts of current and legacy mining sites. This is a mining site which actually extracted arsenic, and what you end up with at this site is bricks and mortar of buildings on the site that are impregnated with arsenic. So what happens is that rain falls on these former buildings. You can see some of the brickwork here. This rainwater percolates into the bricks, dissolves the arsenic that's actually impregnated the bricks, and you end up with these things called efflorescences, which are arsenic-rich minerals actually growing from the mortar between these bricks. You can actually examine them. You can determine, okay, well, how soluble is this? What happens if rain falls on this stuff? Will it get into groundwater? Will it get into surface water? And what's going on with the breakdown? You actually get some things which are living in these environments, fungal spores and the like. So this is just understanding former mining sites, and this understanding can also be applied to future mining as well. We can also look at things like how much energy it takes to produce metals and minerals and different types of mineral deposit. These are all rare earth element deposits, looking at future sources and looking at how energy intensive extraction is going to be from each of these different sites. You can see some sites are low energy intensity, other sites are high energy intensity, and this all feeds into the environmental impact of mining. On the converse side of things, if we look at mining waste, this is a mineral deposit called Mount Keith in Australia. It's a nickel mine. If you look at these are tailings, this is just fine-grained waste material. But these tailings, as they're sat at the Earth's surface, they're actually naturally sequestering CO2. They're just sitting there, they're reacting with the atmosphere, they're sucking in CO2. It's basically a positive impact of mining waste. We can also see how the reactions within these areas can be enhanced to actually increase that CO2 sequestration. So there's all sorts of things that we can look at and actually help both miners understand their environmental impact, but also turn their mine sites into potentially positive areas from an environmental viewpoint. You can also think about metals once they mine, like life cycles of metals. Here's the metal mining, metal waste processing, and so on. We end up with the metals in final goods, and then we can think about potential recycling, so understanding almost the life cycle of metals and how that feeds into meeting future metal demand. The role of mining in green technology supply chains. So these are lithium-ion batteries. These are all the elements that go into them, and the various forms, and then how they might be recycled at the end. But it just shows or illustrates the variety of different metals that go into individual, in this case, solar panels or lithium-ion batteries that are involved in green technology. We can also do research into how metals are produced in the future. So this is just diagrams showing how copper grades have decreased over time across the world. In other words, we're mining more material and extracting more copper, but the volumes of material we're mining are vastly increased. We can also look at how things have changed in individual mineral deposits over, in this case, a 10-year period, whether they're growing, whether they're shrinking, what's happening to the material as we know it in the ground. We can look at the impact of the risks associated with mining in the future as well. These are just copper, lead, zinc, and nickel deposits globally. What we can do is we can model their locations relative to climate change or predicted climate change, and see whether they're going to have are they going to have water risks as a result of the changing climate in the future. They're going to be in areas of high water stress. Are these mining operations, which we're using to supply green materials and green technology, are they actually threatened themselves by climate change and by the reduction of, say, the amount of water they need to actually operate? Similarly, other types of risks and other things to think about, which is platinum group elements. We can compare the locations of platinum group element resources that will be mined in the future to things like Human Development Index. How is this mining linking to social development, investment and policy perception from a business side, environmental risk and environmental performance. So are we going to be able to produce these platinum group elements in a sustainable way Is it going to help support human development? Is it actually going to be an environmental problem, the extraction of these metals? All of this leads into developing approaches to mining that ensure mining is as sustainable as possible and is beneficial for people both locally and globally. And one question is, what risk does mining face right now? This is a shameless self-promotion publication I recently had out in the Society of Economic Geologists Discovery newsletter, looking at COVID-19 and the global mining industry. What's happening right now? What's happening with things like this is just showing how volatile metal prices have been since the COVID-19 pandemic started, since it was identified, declared as a pandemic, and what's been happening since then. What implications that has for the mining industry, both now and in the not too distant future. So we can think about the future of mining, not just in the kind of medium to long term, but also the short term, and like here on a day-to-day basis in terms of the price of metals. These are the various precious metals. These are various base metals. We can see how the prices react to different events, to shutdowns and so on. And we can actually look at things like this is the amount of unsold material sitting in stockpiles in the London Metal Exchange. You can see zinc stocks. There seems to be a lot of unsold zinc or zinc waiting to be sold, which may indicate that in this case supply is exceeding demand because the demand for zinc has shrunk as a result of economic changes related to COVID-19 and so on. I've shown you a whole lot of information there. One thing is, why have I shown you all of this? What I would say is all the research I outlined in the last few slides have been undertaken by me, with colleagues globally, locally, with students. This just kind of shows the range and knowledge of skills that UNLV Geoscience has access to and is instrumental in developing. We would argue the mining industry needs. Certainly my interactions with the mining industry have been positive in terms of us helping to answer the problems they're facing. And that's what the type of dialogue I certainly would encourage. Equally, the people that do this research, the students, they've gone on to academic positions, gone into industry positions in the mining industry, they've gone on to government positions. We're aiming to produce a pipeline of skilled people that can help shape the future of mining. And it's important that these students have core technical skills, but understand mining and its role in society, which is the entire focus of the first half of this talk. We also need to talk more to the general public about this, I would say. It's an effort that I'm trying to undertake, but we need a general public who understands the role of mining in their lives, the importance of this industry, and how mining has a role in the mitigating the effects of climate change. We need to communicate this, the people that we need to communicate this need to understand it themselves, need to educate others. Hence why I'm talking about the need to go beyond core skills. Otherwise, what happens is mining ends up as we were in the second slide of my talk, dirty, problematic, and an old defunct industry. And that is not the case at all. So just a few concluding thoughts before I run out of time. Mining is essential to modern society, but it's going to be increasingly important if we try and do anything about climate change. We all need mining. But the message needs to go beyond mining. We can't just preach to the converted. We need to educate policymakers, the general public, on the importance of mining and its role in our lives. And this is important because people just state we need to have X target by X date, but they don't realize the material implications of that and how we can actually do that. Future challenges faced by the mining industry is not just technical, but environmental, social, and governmental. And I would argue the students and researchers we're developing at UNLV can help meet those challenges as employees by undertaking research and by more. The people that I would hope the mining industry could see as valuable, we're certainly trying to produce at UNLV. I would say certainly dialogue is essential between all parties here, between the mining industry, between academia, between government, between people who are being affected both positively and negatively by mining. We need to understand each other's problems. We need to create solutions together to ensure that we all benefit, but not just locally proximal to a mine site, but globally from the efforts of the mining industry. And just a few acknowledgements. I couldn't have done anything at all without the hard work put in by colleagues and most importantly students. These are a range of students I've worked with over the past few years at UNLV and my time before that, just to acknowledge their contributions to the research that I've outlined in the last few slides. To emphasize that research was undertaken by people like this working in a university setting. I haven't shown anything in that last half of the slide that doesn't have the name of myself or one of my students on it. And similarly, just to acknowledge a few of the students, a couple of postdocs as well. They're not only current students, but students who've gone on to the mining industry in Sweden, working in Australia, and various parts of the world. So actually producing people who can go out there and who can do exactly the things that I've talked about in the last half of the talk. And that's it. If anybody has any questions, you can always ask now. You can always email me. Happy to pass on papers, happy to pass on this PowerPoint, happy to continue this discussion in any way people would like. And with that, I'm going to stop sharing my screen.
Thanks so much, Dr. Jowitt. We really appreciate it, and we appreciate your time in preparing this and presenting it to everyone here today. There were a few questions that came in the chat. So I'm going to see if we can cover them really quickly. There are about 4 that I wrote down. So the first one was, has any analysis been completed on the reduction of GHGs by domestic mining to support domestic manufacturing versus the use of international sources for raw materials and manufactured end products? And they said, think globally, mine locally.
I'm not sure about the comparison between domestic and global, or, domestic and mining outside of the US as a comparison. Certainly, there's been quite a lot of assessment of mining as a function of the grades of materials that are being mined, and you could apply that to look at domestic mining versus international. So that's something that certainly is very possible with the data we have already and the data that mining companies report. And certainly if somebody does that research or somebody is interested in us doing that research, we can certainly do that, because I'd certainly support a case for domestic mining potentially being more environmentally friendly than international mining.
Great.
But I think it's a possible, but I can't think of any studies that have done it as yet.
Okay. So the next question is, will the density of rare earth metals in mined ore go down over the next few years and price per kilogram rise as more and more rare earths are needed for electronics and motorized electric vehicles, excuse me?
It's a difficult question. Certainly the demand for the rare earths is increasing, but what we're seeing is that there's a lot of potential rare earth element deposits out there already that are known. And it's a balance between, the price being high enough for those to be developed and the price, it's difficult. I would say certainly the price is likely to go up, and the price will go up for certain rare earths rather than others, because there's a bit of a balance problem in that we have an oversupply of certain rare earth elements, undersupply of others. One example to look at now is Mountain Pass just down the road in the I-15, where they're mining and operating, but as far as I'm aware, they're still doing the majority of processing in China because the economics aren't good enough to do the actual processing in the ore here in the US. So I think even with the operations like that are being successful, they're not 100% successful because the market for the rare earths isn't as buoyant as it could be. It's difficult with the rare earths because a lot of rare earth element supplies from China, and they control the market. In some ways, there's other deposits in Australia that are being mined now and so on, but it's still very much a China-centric market in terms of they produce a lot of rare earths and they also use a lot. That's where a lot of the rare earth element demand is. They almost have a cornered market. So it's difficult to predict.
Okay. And then the next was, where can the world source large amounts of pure water to process mined ore into pure minerals useful for electronics, motors, batteries, etc.?
It depends where it depends where you are. There's if you're mining in the Atacama in Chile, where hasn't been any rain for the last 100 years or something, what you do is you build a big desalination plant down by the sea. I think it's Antofagasta, and then you pump the stuff up 4,000 meters because you need the water. So the desalination is one possible thing, but then you run into issues with energy and the like. So it's a difficult equation to meet. Certain mines are fine with water; they have plenty. Depends where you are in the world. But other mines, you either develop technologies that use less water, which is difficult, or you build large-scale desalination plants and the like, which are both capital intensive and need lots of money, or they need lots of energy. So it's difficult. I don't know if you can actually source that easily. That's one of the problems that the mining industry is going to face going forward.
Okay. And then we'll take 2 more questions, and then we'll end. The next one should be fairly easy to answer. Are ESG topics covered as part of the geoscience curriculum at UNLV?
Emily, yes, they are. Certainly, I know Matt, who's on the, I believe, on the talk on the Matt, who's chair of the Department of Geoscience, and he's on this talk right now. Covers climate change topic. I cover ESG topics in my economic geology courses. I think it's important for students to, not just have those core skills, but actually to think about the sustainability of mining, environmental, social implications, and things like that. So yes, we do.
And then we'll take the last question from Ariel. David, if you want to email your question to Dr. Jowitt or send it on Twitter, he can get back to you on that. But I just want to be conscious of time. So Ariel's question is, in acknowledging there are unavoidable environmental impacts from mining activities, have you encountered any good ways to counterattack environmental justice talking points?
I'm not sure about counterattack, but I think one thing to do is just have open dialogue and talk to people. And on the kind of environmental side of things, it's difficult because you can end up with there's a famous example called Rosia Montana in Romania, a big gold deposit. What you have there is a situation where the locals actually, they've weighed their opinions up, and a lot of the locals actually want mining to go ahead or wanted mining to go ahead. But other people, some of the locals didn't because they thought that the environmental risk outweighed the kind of the benefits from employment and the like. And then you get other people from outside who are actually arguing against it, who might have might visit there as tourists, might be things like that, who actually kind of have peripheral interest in the area that might be the focus of mining, but certainly have a very vociferous say on it. So I don't think there's any good ways to counterattack, but I think the key thing is to have open discussions with everybody involved, with all stakeholders. And we're seeing that in the mining industry more and more. And I think basically that has to be the way forward. And I think there needs to be just a discussion over local impacts and global and local benefits and things like this, because we need to consider things. You can't just say, oh, we're going to mine here because we need stuff to combat climate change, because that discounts all local impacts, and that's a very difficult and dangerous thing to do.
Awesome. Ariel did clarify that it should have read counteract instead of counterattack. So yeah.
Some people might argue counterattacking is a viable term.
Yep. And there are a couple more questions that came in, but I do want to just be aware of everyone's time. And so please do feel free to email Dr. Jowitt. He is a great resource and very knowledgeable, as you can all tell from the presentation, and is more than happy to answer your questions. And give his opinion and expert advice and research about this topic that is important to all of us. It's a critical piece of Nevada's economy and the global economy as well. So thank you so much, Dr. Jowitt, for your presentation. We really appreciated it. We enjoyed having you here today. And again, this has been recorded, and it will be available for viewing on the College of Sciences website after probably by mid next week. That's usually takes about a week to get it up. So I will look forward to seeing you all hopefully at our next lecture on November 25th with Dr. Ashkan Salamat. Thank you.
Thanks a lot. And yeah, if anybody does have any questions, you can always Google me, and I usually turn up at the top of the search list because my surname isn't very common in Las Vegas.
Thanks, everyone. I'm going to stop the recording.